Okay, today we're going to demonstrate this CAD importer that we've built for importing fluid models. This comes as a SimulationX add-on, which you can see in the right-hand panel over here. The first thing we do is select the CAD assembly that we want to import, and in this case I'm going to choose this model right here. And once you've selected it, we press the Start Import button to begin, and it will give you a message extracting the CAD geometry. This can take a couple of minutes for large assemblies. And this shows the model that we're going to import, or at least we're going to import part of this. We're going to focus on these refrigerant pipes going up to the compressor, the discharge pipe to the condenser itself, and then the refrigerant pipe going back to the thermostatic expansion valve. All right, so a few minutes has passed and the CAD geometry is now loaded. So let's walk through the import process. You can see there's 3 tabs up here. First on this geometry tab, that's where we imported it, and now we're on to components. There we see a tree view of the assembly, breaks it down into its various sub-assemblies and parts. And so we're just going to pick out the ones that are relevant for us today, also partially because of the way that this geometry is built using shells and so on. So we're going to start with the compressor, and to check these boxes here, we first need to uncheck the overlying assembly, and you can see the preview of that assembly changing in our preview window here as we go. So I am going to take that compressor right there, just deselect everything else so we're clean. I have a clean slate. We just did that compressor. Let's move on to the condenser. So this condenser here, we're going to take it as it is, and you'll notice as well, I forgot to do this, I'll have to go back to the compressor in a second. There are 2 buttons down here once we've chosen to import a part. There's a Browse Library button and Obtain Parameters. So the first thing we need to do is to browse which component this is. So I'm going to choose a microchannel heat exchanger from our heating cooling library. And once we've selected a component to be imported for that part, then we can press Obtain Parameters if that part is supported, and we will receive the parameters of that component. So it reads automatically what the depth, the height, and the width of the heat exchanger is, how many tubes it has, and then you can see down here as well, there are some fluid selections. And this is because the heat exchanger model is compatible with the pneumatic, the hydraulic, and the thermal fluid library. So we need to choose which fluids we want on each side. On the fin side, we're going to have pneumatics. We're just going to have an airflow on that side. On the tube side, however, we're going to be having a refrigerant. So we need to change this to thermal fluids. I'm going to choose the table-based fluids for this import. And that one's now all set up. Since I forgot it, let's go back to that compressor. You can see it's still not yellow or green, so we still need to choose a part here for the compressor. Let's go to the thermal fluids library, take a look at the work and power machines, and grab a volumetric transformer. So that has now become yellow, meaning we have selected a part for it, but we don't have the parameters yet. And we can see for the condenser, it's already green because we also have the parameters. Let's move on to the piping. So on the piping side, we have 3 pipes that we're going to focus on: the compressor discharge pipe, AC high pressure pipe assembly, and the AC low pressure pipe assembly. So one by one, we'll start by checking this off, going to our library and choosing the pipe element from thermal fluids. And when we then press the Obtain Parameters button, it's going to find out what the inner diameter of that pipe is, what the length of it is, and the number of bends. Now, the pipe in the thermal fluids library considers 90-degree bends, so the algorithm is set up in a way that it basically finds the total number of angles and divides by 90 and rounds it to the closest number of equivalent 90-degree bends. You can also see here the confidence rating of the judgment that was made on the geometry. So that's the compressor discharge pipe. Now let's take the AC high pressure pipe assembly. Same process, go to thermal fluids, find our pipe element, obtain the parameters, and onto the third one, low pressure pipe assembly, thermal fluids, the pipe. Okay, obtain parameters. All three of those are now green, and I think the rest we're going to leave. We've got our three pipes, we've got the compressor, we've got the condenser, so we can build that partial model right here. So we then switch to the connections tab, and the first step is to press refresh connections to load the full table of possible connections. So we see here our compressor assembly with the two thermal fluids, a mechanical and a signal port, our condenser with the two pneumatic connections and the two thermal fluid connections, and then our three pipes, each with two thermal fluid connections. And so now we basically can set up the connections in here. So starting from our low pressure pipe, port A here is the inlet, port B is the outlet. So we're going to connect the output of the low pressure pipe to the input of the compressor assembly. That puts us up here, and we can now see that port A of the compressor assembly has become inactive because it's connected. So we now take the output of the compressor and connect that to the compressor discharge pipe, port A. And from the compressor discharge pipe, we connect it to the inlet of the condenser on the tube side. And from the outlet of the condenser tube side, we connect that to the high pressure tube inlet. And that should be everything set up. So we now press generate model. And those components, parameters, and connections will be input. Okay, so now we can just minimize this and take a look at the model itself. So a couple of things can be placed in a different spot. It does take the geometric location of the element within the geometry into account when it's building the model, but sometimes things still need a little bit of adjusting. So let's just set this up a little differently here. Okay, and to make sure everything is working, well, first we can just double click and do some spot checks. So if we take, for instance, the low pressure pipe assembly, we see here the throttle length in millimeters, the pipe length in millimeters, the internal diameter in millimeters, number of equivalent 90-degree bends. So that's all been imported correctly. So let's set up a simulation to make sure it works. We're going to take a pressure source element here as our inlet boundary condition, and another pressure source element down here as our outlet boundary condition. So before we go any further, let's just double check what fluid we have here in this connection. So we're using R134A. That'll be fine for our experiment. Let's begin working on setting the boundary conditions. So we'll use 3 bar and 25 degrees Celsius as the inlet boundary condition for going to the compressor. And as an outlet boundary condition, we'll use 12 bar. And rather than have a fixed temperature, let's set this to be initial value so that we're calculating a dynamic temperature based off of the system behavior. Next, we're going to need some air components and airflow through our heat exchanger as well. So we're going to use the heat and cooling library, and under gases basics, if we drag in a pressure source, that can be our air inlet. An exhaust element can be our air outlet. And then we will use this flow source here as a fan, as some sort of flow source for our air going through the condenser. We're about ready to run a simulation just to test everything. So first let's set the solver here to have a stop time of 10 seconds. And then we'll press start just to make sure everything's working okay. So the symbolic analysis is now running. The simulation begins, and 10 seconds. All successful. So usually though, the results for this kind of a system are viewed best within a pH diagram. So let's take a look at adding a pH diagram. That can be done here with the thermal fluids library. And under diagrams, you'll find a state diagram. We'll add that as our initial state point. And then we're going to add various state sensors afterwards. So this is state point 2 before the compressor, state point 3 after the compressor, state point 4 before the condenser, state point 5 after the condenser, and state point 6 at the outlet. Now I'm going to just have to go back for a second here and just add the correct index for each of those state points. So 3, 4, 5, 6. So the next step is to add a visualizer. In particular, we're going to need a multi-chart. We'll just drag it down to this corner so that we have a bit more room. And we need to connect this multi-chart to the state diagram by double-clicking, finding that state diagram and selecting the pH data. And finally, just going into the state diagram itself and making sure the settings are correct. So we have 6 states that we want to diagram. It's not a cycle, and as a minimum value on the p-axis, let's choose 1 bar. 100 bars fine for the maximum. Let's leave the rest like that. Reset our simulation and run it one more time. And there we have our simulation and process diagram.